Throughout his 13-book mathematical treatise of around 300 BC, called simply The Elements, Greek mathematician Euclid of Alexandria likely borrows a great deal from earlier, probably primarily Pythagorean polymaths, although Pythagoras, 570 till 495 BC, is himself cited as the source for only two axioms, recalled to this day as Book 1, Propositions 47 and 48. The postulate premised in these propositions is taught to this day as one of the earliest and most integral discoveries of a universally generalizable mathematical axiom in human history. The fact that Pythagoras studied trigonometry so much that he discovered a rule that applies to all right-angled triangles was, at that time, presumably unprecedented. This rule, called still the Pythagorean theorem, describes the fact that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the sides. Prior to Pythagoras, similar generalizable observations had been posited in the Chinese Zhubi Zhuanjing from sometime between 1046 and 771 BC. However, nowadays, Pythagoras remains credited in the history of Western civilization with first recognizing the universality of applicability for this general observation. What makes the universal generalizability of this arguably earliest mathematical axiom appear additionally miraculous is the fact that in almost all cases, aside from those called the Pythagorean triples, the measures of the sides of such triangles are not whole number sums, but inequalities, with remainders of decimals or fractions. The particular example of a Pythagorean triple given by Euclid is nowadays the most well-known format for such: a triangle with two legs, one length 3 units, the other length 4, around a right angle, opposite which is a hypotenuse of length 5, connecting to the 3-unit length leg at an around 54-degree angle, and to the 4-unit length leg at a roughly 36-degree angle. The closest approximations of these exact angles are 36.87 degrees and 53.13 degrees. This example of a Pythagorean triple right triangle is also the sole triangle with edge lengths that proceed in arithmetic progression, making it a special case of right triangle as well. Like all Pythagorean triples, the right triangle of lengths 3, 4, and 5 is also Hieronian, named for Hero of Alexandria, whom lived from 10 until 70 AD. It thus has a total area that may be expressed in whole integer number sums as well. The so-called 3 to 4 to 5 ratio Pythagorean triple, or simply the 3, 4, 5 triangle, was long held as sacred among occultists and underground practitioners of precursors to modern science. However, it was not until the geometric work of Johann Kepler, 1571 to 1630 AD, that a smaller and even more fundamental triangle in this same sequence was discovered. Named after him, the Kepler triangle preserves the ratio, roughly 36 to 54, of the non-right angles that occurs in the usual 3, 4, 5 Pythagorean triple. However, expresses these angles on a similar Pythagorean triple with shortest leg length equal to a single unit. Now, when you render a Pythagorean triple thus, with angles approximately 36, 54, 90, and the shortest leg length equal to a single unit, another Greek letter variable, symbolizing a certain irrational number sum, appears. This sum has been translated using the Greek letter phi since at least mathematician Mark Barr, 1871 until 1950 AD, expressed it as such after the first initial of the Greek sculptor Phidias, 480 until 430 BC. However, from ancient times, this sum has been known of and called simply the golden ratio. The golden ratio is expressed for one line segment divided into two, such that the length of the shorter is relative to the length of the longer, in the same ratio as the length of the longer is to the length of both the shorter and longer legs recombined into one. In short, the golden ratio is best expressed as A plus B over A equals A over B. A basic example would be the ratio 1 to 2/3, but this would only be an approximation of the actual golden ratio that is expressed exactly as the irrational sum of 1 plus the square root of 5 over 2, or roughly 1.618. The Kepler triangle model of a Pythagorean triple has legs equaling 1 and the square root of phi, and a hypotenuse equal to phi. The squares of these legs therefore unfold as 1 squared, phi, and phi squared, a geometric progression including the golden ratio. Whether in the form of the eponymous Pythagorean triple of ratio 3, 4, 5, or as a product of the golden ratio in the form of the eponymous Kepler triangle of 1 to phi to square root of phi, it is well documented the rising angle of the outer casing stones of the Great Pyramid of Khufu, called in Greek Cheops, in the Egyptian Giza necropolis, is about 54 degrees, or nearly identical to the rising angle in both the 3, 4, 5 Pythagorean triple and Kepler triangle. This means, ostensibly, the Great Pyramid at Giza is both a Pythagorean pyramid and a Kepler pyramid, both being merely extensions into 3 space of their two-dimensional counterparts, hence discussed. As an example of a Pythagorean triple and a Kepler triangle, the Great Pyramid at Giza provides humanity with a unique template for calculating these geometrical concepts, as the pyramid's original designers must have as well. Consider a nearly equilateral triangle with a base length of 2 units, base angles of around 54 degrees, a rising hypotenuse of length phi, and a peak capstone angle of around 72 degrees. If this 54 to 72 to 54 degree triangle is bisected vertically from the midpoint of its base to the crux of its 72-degree capstone angle. The length of this line will be, as previously posited for such a Kepler triangle, the square root of phi. So, in this model, we see the same measures as the Great Pyramid of Khufu in Giza, expressed in their smallest common denominator as a Kepler triangle. To make this 54, 72, 54-degree triangle even more accurately significant of the Khufu pyramid, we may simply attach 4 such triangles along their hypotenuse edges around a square base with area of 4 square units. This 4 square base unit is significant in itself, and we will return to it in a later segment of this lecture. For now, it is sufficient to note the height of each side of such a Kepler pyramid will be phi, when the height of the pyramid's apex above the center of its 4-unit square base is equal to the square root of phi. Now, in a Kepler pyramid, like a scaled-down version of the Khufu pyramid at Giza, where the rising angle off the base length is approximately 54 degrees, and where the length of this base leg is given as being 1 single unit, the height of the pyramid's sides is always going to be given as phi, and the height of the pyramid's apex point likewise always given as the square root of phi. This is the nature of the golden ratio as a mathematically irrational number sum. It expresses certain peculiar character traits unique to itself, as well as others that it seems to share only with a few other integers, those being of the lower value counting set, such as the 3, 4, 5 Pythagorean triple, and its like in multiple higher factors. Although no short supply of proportions with sacred geometrical significance may be derived using the golden ratio, the earliest attempts at applying it to the method of squaring the circle involved using a Kepler triangle to define a single large square comprised in turn of 4 smaller squares in a standard Cartesian quadrant plane. The Kepler triangle was then plotted into this base 4 square as sharing its base 1 unit length and the right angle at the 4 square's axial crux. The 4-unit square then yields a circle by rotation that has a radius of the square root of phi. While the circumscribing circle cannot, as explained before, share an exactly identical area with the base 4-unit square, it does define a condition of similitude in size scale that is quantifiably negligible in its distinction of one apart from the other. Another way of looking at this may be as such. If a square-based pyramid is placed on even ground on the equator, and its rising angle is around 54 degrees, then the shadow of its apex capstone will fall around and upon that base to a distance equal to the pyramid's height in a cycle throughout the year. When one considers the premise of a prehistoric Giza equator, one may begin to wonder if the Great Pyramid was not constructed as a means of squaring the circle, using its structure as a sundial and its annual shadow as a geometrical proof. Further speculations on this line of reasoning also include examining the relative sizes of our Earth and its moon by placing the circumference of Earth at the center of the larger square and that of the Earth's moon such that its centroid would overlap the pinnacle of the square root of phi height triangle. These are obviously speculative studies in sacred geometry, however, and not exact science.